Hey guys, welcome back. Today we're going to learn a new way to compute maximums and minimums. So before we do, let's review what we currently know. What we currently do for maximums and minimums is we do our first derivative sign chart, and let's say it goes like this. Okay, if the derivative is 0 or undefined, okay, then we have our critical points, as long as there's actually a point there, and that would mean that I need to know what the original function is. And then after we know our critical points, if the sign changes from positive to negative, we have a max. So this would be a local max. And if the sign changes from negative to positive, we would have a min. Okay, well, that's the most common method for doing it. But today we're going to learn another method which is sometimes faster, okay? So, still finding maximums and minimums, but using an alternative method. Okay, you guys don't have whiteboards in front of you, but try this on a piece of paper. Take a minute to think about what this really means. Okay, first derivative is 0. At 3 something. I don't know where it is, okay? But at some point 3, wherever, 3, 1, 3, 2, whatever, there's a point. And at that point, the derivative is 0. Okay, what does that mean? Okay, derivative of 0 means it could either flatten out, kind of like this, or derivative of 0 means it could be a max or a min. That would be a derivative of 0. This is a derivative of 0. Okay, so we have a derivative of 0, and now I want you to also include this. At that same spot where the derivative is 0, the second derivative is negative. Well, second derivative negative, that means concave down. So for both of these things to happen at the same time, this would have to be a max. And that is called the second derivative test. Basically, if your first derivative is 0, but your second derivative is negative, it has to be that there's a max right there. Okay, here's another one. Well, that's the same thing, sorry. Okay, for this one, first derivative is 0, so you know it's a max, min, or flattens out. But the second derivative is positive. Okay, first derivative 0, that means either it flattens out like that, or it's this or this. Those are your choices. Well, this guarantees second derivative positive, it's got to be concave up. So what's happening right there at that negative 2? You have to have a minimum. So that's the second derivative test. Here's how it works, okay? If your first derivative is 0, and it has to be 0, it can't be undefined. So if your first derivative is 0, but your second derivative is positive, then you know you have a minimum. If the second derivative is negative, then you know you have a maximum. Now, I will ask you on your next test, and they often get around this on the AP exam, by forcing you to give a process instead of the final answer. So I will force you to use the second derivative test on your next test. Otherwise, you really could always use the first derivative test or first derivative sign chart. So I will have to force it. I'll say, show your work using the second derivative test. So again, what does that mean? You find the first derivative still, you find your critical points, and then you plug those critical points into your second derivative. Okay, here's an easy example. Okay, if I say using the second derivative test, then instead of doing a first derivative sign chart, you're going to still find your critical points using the first derivative. Then you're going to find the second derivative. Whatever critical points you find over here, you're going to plug them into that second derivative. If you end up with a positive value, you'll say that you have a minimum. If you end up with a negative value, you'll say you have a maximum. Okay? So let's give this one a shot. So first, we find our critical points like normal. Find the first derivative, then set it equal to 0 and maybe factored, and then set each factor equal to 0, and we'd get that our critical points are 0 and 3. Now, instead of doing our typical first derivative sign chart, although that would still work, instead we're going to now do the second derivative. So we find our second derivative, and when would you do this test instead of the first one? Basically when it's easy to get the second derivative. If the second derivative is easy and quick to get, that's when I would use this. And now, plug these critical points, oops, that was a mess. Plug these critical points into that second derivative. Okay, so I plug in 0 and I get a negative answer is all that matters. And if I get a negative, my second derivative is negative, that means concave down. And therefore, this is a maximum at 0. Okay? And when I ask you to justify it, you'd say maximum at x equals 0 because the first derivative at 0 is 0, but the second derivative at 0 is negative. That's how you justify it, and you have to justify formally. Okay? Now, how about at 3? Plugging in the 3 into my second derivative, I get a positive answer, which means concave up, which means this is a minimum. So I'll say formally, minimum at x equals 3 because f prime of 3 is 0 and f double prime of 3 was positive. That's how you have to justify using the second derivative test. Okay? Whereas, by the way, if you were using your first derivative sign chart and I asked for formal justification, it's kind of a pain. You have to say first derivative equals 0 or undefined and changes from positive to negative, and then you can say max. That's a lot more to write. So the second derivative test is pretty easy. Again, I would use it pretty much only when I'm told in the directions, or if the second derivative is easy to find. Okay? Now, notice that it has to be a derivative of 0. It doesn't apply if it's a derivative that is undefined, and let me explain why. So the reason it has to be only a derivative of 0 is that derivative of 0 ensures that you have a smooth curve. So remember, first derivative 0 could have been this, that's a first derivative of 0, or this, okay? So as long as we get the second derivative as positive, it's definitely a min, and as long as we get second derivative negative, it's definitely a max. If the second derivative, though, isn't either positive or negative, and you get a second derivative that is, if your second derivative ends up being 0, that's going to be this, and that doesn't guarantee anything. So the second derivative has to definitely be either positive or negative to ensure the second derivative test. You can't get 0. Okay, it's got to be one of these two. Well, the other qualification is the first derivative has to be 0. It can't be undefined, because undefined would mean like a sharp point. Let's say maybe something like this. That would be a derivative of 0, okay? And that's still a minimum, and we would still find it if we had a first derivative sign chart, but the second derivative shortcut wouldn't work because this is not a derivative of 0. This is a derivative that's undefined. And if you'll notice, what is the second derivative here? It's concave down, so it's a second derivative that's negative, but a second derivative negative is supposed to mean maximum, and that's clearly not a maximum. So to summarize, the second derivative test is only for derivatives that equal 0, they're not undefined, and it has to be that the second derivative is either positive or negative, not 0. So I'm going to go back to the page that has the rule for the second derivative test. Here it is. So it's very easy, just don't confuse it with other things. Second derivative test is for finding maximums and minimums. It's a shorter way to do it. It still finds maximums and minimums. Okay? The first derivative has to be 0. It can't be undefined. And the second derivative has to end up being either positive or negative. It can't be 0. Okay? So today's homework is pretty short, just using the second derivative test. Good luck.